first thing I want you guys to notice about this video is the color scheme and how patriotic it is. Check out the red, white, and blue. Check out the American flags. Yeah. The second thing I want you to notice is that with Chapter 11, we're going to be looking at areas and lengths, in particular, things like perimeter. So, at the beginning of the chapter, we're going to start with some basic stuff like triangles and parallelograms. We'll move on to things like kites and rhombuses or rhombi, whatever, I don't know, as time goes on. But for now, we're going to start super easy with even something like a square. So, we know the area of a square if we refer to the side length as an S, a square being defined as equilateral, angular quadrilateral. It's the same base times height formula, but since the base and the height are the same, we can just call that the side. We know the area to be side squared. With a rectangle, we just know it to be base times height. So if I were to ask you, given the ingredients below for each of these figures, to find the corresponding area, or area and perimeter, one or the other, we'd be able to do so. I'm not setting you up with impossible problems here. For the purple square on the left, I would take the side length, 2 root 7, and square it. And if we're a bit hazy squaring something involving a radical, think of it as multiplying it by itself. It's 2 root 7 times 2 root 7. That's what it means to square something, right? You multiply it by itself. So also a property of multiplication that we don't talk about too much, but we should identify, is something called a commutative property, which says if I'm multiplying a bunch of stuff, the order in which I multiply those things doesn't really matter. I can group it however I want. So really, when I multiplied 2 root 7 by 2 root 7, I could choose to multiply the 2's to get 4. I could choose to multiply the root 7's. Root 7 times root 7 is root 49, which is just 7. Or the square root and the squaring of multiplying something by itself cancels out, and I get an area of 28. Since I was told that the original units were centimeters, I know that the area here is going to be centimeters squared. Here we have to work backwards, actually. If we want to find the perimeter of the square, what we could do is we could find the side length first, and then multiply it by 4. So if I want to find what the side length of the square is, I can take, I know this much. Side squared equals the area, and I'm told the area is 58. So if I want to find the side length, I can take the square root of 58, see if I could simplify that first, and then notice that I'm only going to be dealing with a positive answer here. Normally I'd get on your case about inserting a plus or minus sign. We don't actually have one of those here. As it turns out, if you break up 58 into its factors, 58 is equal to 29 times 2, both of which are prime. So it looks like we actually can't simplify the radical of root 58. So now when I find the perimeter, when I say it's itself times 4, root 58 times 4, we write that as exactly 4 root 58. And that's about as simple as our answer could be. Don't forget the units are feet. For the problem on the right, the one that's on the coordinate plane, this one's actually a little bit interesting, and it's not explicitly thrown out as what we should do, but we know we have to find the side lengths, and if we have a coordinate plane, we're trying to find lengths, we should resort to the Pythagorean theorem most of the time. If you're desperate enough, you can use the distance formula, I guess, but we don't really need to do that, I hope. I hope by now we see that I could take any of these sides and make it the hypotenuse of a right triangle. And in this right triangle that I've created here, the hypotenuse is part of a triangle with legs length 1 and 4. So 1 squared plus 4 squared equals c squared. I can write this down here, I guess, where we'll call the side length c. This is the Pythagorean theorem, basically. C squared equals 1 squared plus 4 squared. 1 squared is 1, 4 squared is 16. So basically c squared is 17, c is root 17. So if I square the square root of 17, the square and the square root are going to cancel out. I'm just going to get an area of 17. For perimeter, I'm going to get 4 root 17, which of course is simplified because 17 is a prime number. So here are some theorems that are going to be, or not theorems, sorry, postulates actually, which means we're not going to prove them. But they should make sense to us anyway. It should be very kind of instinctual to us that the area congruence postulate is true. If two polygons, really 2 or more polygons, are congruent, then they have the same area, or I could say equal area. Since area is some kind of measurement, we would say equal instead of congruent. And then look at this. Look at this guy. The blank addition postulate shows up again. It used to be angles. It used to be segments. But basically, even in the case with area, they all boil down to the same thing, which is that the sum of the parts equals the whole. This allows me to take a weird shape like this thing below. I can count up the number of sides and call it an n-gon, but it'd be the ugliest n-gon of that sort I've ever seen. What we should probably do instead is break it up into different shapes. Smaller shapes that I can actually find the area of, and then take the sum of those areas. This is how I would find the area of a composite figure. Call it a composite figure because it's composed of things that are smaller and simpler than it. So, if I were you, I would pause it and try to find a way to break this up. There's more than one way. Try to find the areas of those and then add them up. Take a moment to pause and try it on your own. I'm going to go in 3, 2, 1... Well, I have broken this shape up thusly into basically 3 rectangles. A square is one of those rectangles, but that's besides the point. If I just find the areas of each of these things individually, this is a 3x4 rectangle given an area of 12. I'll worry about the units later. This guy on the right is a 3x3 square, so it has an area of 9. And then this thing in the middle, well, if I see that this entire length is 4, and this part of it is 2, then the remaining part has to be 2 as well. Similarly, if I look at this entire base as 8, with this part being 3 and this part being 3, then the remaining middle piece, in order to add up to 8, has to be 2, giving this thing an area of 4. So altogether, the composite area of the shape is 12 plus 4, plus 9, oh, it's the worst 4 ever, and a pretty bad 9 also, which gives me, let's see, 16 plus 9 is 25 inches squared. So now we're getting to the polygons that we actually see in the title here. Triangles and parallelograms. Triangle I know you know. Parallelogram you might. But just to shed some light on how we get its area, which is actually astoundingly simple, imagine taking this triangle and placing it here instead. Basically just pick it up and move it as though it's going to fill in this gap here and leave me with what is essentially a rectangle. So if I were to just kind of relocate that piece, the area of the rectangle that I have would be the same as the area of the parallelogram that I started with. What is the area of a rectangle? It's base times height. And guess what? That's also true of a parallelogram. Base times height. And keep in mind what the base and the height actually are. The bases are going to be the things that are opposite and congruent and parallel to each other. And the height is going to be the segment that connects the bases that's perpendicular to them. Just make sure not to confuse your ingredients in the future. The area of a triangle, I don't know if you ever were demonstrated why this works the way it does, but imagine if I kind of doubled each piece of the triangle as separated by the height. It would essentially make a rectangle. Like on the left I have the white empty piece, which I'm shading green right now, is congruent to the already yellow piece below it. If I do the same thing with the right half, I make a rectangle. Again, another rectangle. So what's the area of a rectangle? It's base times height. What did we just do to make it a rectangle? We doubled it. So the original triangle, if we undouble it, was half of this, thus giving us the formula 1/2 base times height. A lot of formulas for these things come just from shimmying the pieces around. If you want to try the problems in the bottom, I recommend going for it, but I'm doing it now. If we're being asked to find the area of this triangle, we have to identify what the base and the height are. Base is 21, B is 21, the height is 8. This is explicitly spelled out for us. So if I want to find the area of this thing, the area is 1/2 21 times 8. Well, half of 8 is 4. 4 times 21 is 84. We don't have units, so we're just going to go with those. If you're asking yourself what role the 10 and the 17 played in this, none. It looks like they played virtually no role in this at all, which is fine. If this problem asked you about perimeter or something, well, then the 10 and the 17 would be relevant. If we were given a different altitude in the triangle, the one that connects to the base that's 10, or the leg that's, sorry, the side that's 17, well, then maybe those would be relevant. But for the altitude that we have, the base that it's perpendicular to is 21. So we would use the 8 and the 21, we don't care about the rest. Similarly, for this parallelogram on the right, 30 times 17. Those are the only two measurements we care about. Because this is a parallelogram, it's just going to be BH, which is 30 times 17 which is 510. Do 17 times 3 and then add a 0. The rest of this video is just going to be these practice problems and then some suggested practice problems from the textbook. So whenever you're ready, pause it and go for it. But I'm going now. We should identify that this shape on the left is a parallelogram. There's a lot of ways to do that. I can just count it out and see that this is 5 and this is 5. I see they're parallel as well as congruent, obviously, because they are horizontal. I could do some stuff about these other two pieces too, if I use the distance formula or whatever, but we're good. It's a parallelogram. We have enough there. So, I see that the base is 5, because I can just, would we count it out? That's fine. I can see that the height is also 5. So that just gives me an area of 25. Don't work too hard on this one. Don't try to find the lengths of these diagonal-looking pieces if you don't have to. We have a base, we have a height, we can just use it. We're good. For this guy on the right, I would chop this up into a square and triangle. The square obviously has an area of 49 meters squared, whereas the triangle has, if I were to look at it like this, where this is an altitude and the base is actually vertical here, and is 7 meters. Well, the altitude in this case, the height, would be the remaining piece of the 11 meters that we're told the entire shape is in length. So if I subtract the 7 on the base from this 11, I get that this piece is 4. So this area is going to be 49. Well, let me write it like this first. Let's get fancy. We're dealing with the area of a lot of pieces, and it helps to use good notation. So I can say the area of the total. It's a bad notation. You'll see why in a second. A sub b, area of the big thing, is equal to the area of the square plus the area of the triangle. So if I can identify what those pieces are, then I'm good. The area of the square is 49. The area of the triangle is, let's see, 1/2. Base in this case is 7, and height is 4. That's 28 times 1/2, or divided by 2, so 14. So 49 plus 14 gives me an area of 63 meters squared. Remember, whenever you're given units, you should totally use them. Here we're told that things are in meters, so we know the area is going to be meters squared. The shape on the right is a composite figure. It's a triangle and a rectangle and parallelogram put together. If I use some congruence properties of quadrilaterals, I've pretty much figured out the dimensions here, and now all that's left is kind of figuring out the area using the formulas. So I'm going to do some head work here, or some verbal work, I guess. The area of this triangle is going to be 1/2 base times height, which is 1/2 7 times 9. So 63 over 2, which is approximately, I don't know why I started to say approximately there, sorry. It's 31.5. The rectangle in the middle, or at least the parallelogram looking thing, this is, I'm now picking a different color, 3 times 9, which is 27. The parallelogram on the right, here we don't actually have the height of it, if I look at the 9 and the 9 as the base. So I have to do a little bit of work and say if the entire length of the thing is 16, and part of that is 7, and another part of it is 3, then the remaining part is 6. So the area of this parallelogram is base times height, which is 9 times 6, which is 54. So if I add these things up, I get the total area, which comes out to 112.5. So originally I was going to do 11.2 in this video also, but it's running a bit long, so I'm going to stop it here. Just note that the top half of this document, the first set of pages, the 723 to 724, that's going to be the associated 11.1 suggested homework. So give that a shot, and that concludes our lesson.